Okay, so again we've got some more problems relating to Module 2. In this case it's a problem about the gas laws. So question says, for a fixed number of moles of an ideal gas, sketch plots of, first of all, pressure versus volume at constant temperature. Okay, so our first plot will be pressure versus volume at constant temperature. Okay, and this is basically what's known as Boyle's law. And what Boyle's law states is that the pressure is inversely proportional to the volume at constant temperature. Okay, and what that looks like if we plot a sketch of it is the following. If we put pressure on the vertical axis and volume on the horizontal axis, then an inverse relationship looks something like this. It's a bit of a wobbly line. That's basically what it looks like. As pressure increases, the volume decreases, and conversely, as pressure decreases, the volume increases. That's what an inverse relationship of this form looks like. And it's fairly straightforward to understand why that might be the case. If we imagine that we have a sample of an ideal gas in a container that has a movable piston as a lid, and we can move the piston, that's our piston, we can move it in or out. Okay, and if we have a fixed mass of gas or a fixed number of moles of gas in our sample, then if we were to move our piston in, we would decrease the volume. Okay, so by moving the piston in, our volume would decrease. What would happen to the pressure? Well, because the volume has decreased, the gas molecules in our sample will continue flying around at the same speed because they're at constant temperature and therefore have constant energy. But because the volume is smaller, there would be a greater number of collisions between the atoms and the molecules of the gas, and between the atoms and the molecules of gas and the sides of the container. And remember that the pressure that's measured is the result of the collisions between the atoms and molecules of the gas and the sides of the container. So because the number of collisions per unit time would increase when the volume decreases, the pressure itself would increase. Okay, which is an inverse relationship. The pressure is inversely proportional to the volume. And we can do similar reasoning for the opposing change. If we were to have our fixed volume or a fixed amount of gas in a container with a movable piston as a lid, and if we were to consider increasing the volume by moving out our piston under conditions of constant temperature, what's going to happen? Well, the same amount of gas will be present in our sample, but because the volume is greater, the number of collisions per unit time will decrease, and the number of collisions per unit time between the atoms and the molecules and the side of the container will also decrease. So as a result, the pressure will decrease. Okay, so that's a rationalization of Boyle's law, which as a graph, when sketched, would look something like this. That's what an inverse relationship would look like. Okay, the second graph that we have to look at is pressure versus temperature at constant volume. Okay, so we've got pressure versus temperature at constant volume. Pressure versus temperature at constant volume. And this is an example of Gay-Lussac's law. And what Gay-Lussac's law says is the following. pressure is directly proportional to temperature under conditions of constant volume. And what that mathematical relationship would look like if sketched on a graph would be the following. Again, if we put pressure on the vertical axis, temperature on the horizontal axis, then we would get a linear relationship between pressure and temperature. As temperature goes up, so too does the pressure. And remember, when we're doing calculations on the gas laws, the temperature is always in Kelvin, such that the pressure would become 0 at a temperature in Kelvin of absolute 0 as well. Now, what's the rationalization for this? Well, imagine that we have a fixed volume of gas in a container, so that's fixed volume. And imagine that we were to heat our container, so therefore we have an increase in temperature. What's going to happen to the molecules of gas in the container? Well, they're going to get more energy, they're going to get more kinetic energy, they're going to be moving faster, and the collisions are going to be more energetic. Okay, so their collisions are going to become more energetic. They're also going to become more frequent, because if they're moving faster, then they're going to come into contact more often. Okay, so the molecules of the gas both increase the energy of their collisions, and they also increase the frequency of the collisions, both amongst themselves and with the walls of the vessel containing them, which means that the pressure will also increase. Okay, so as the temperature increases, the pressure increases, and you can rationalize what happens when the temperature drops. It will be obviously in the opposite direction. As the temperature drops, so too will the pressure. Okay, so that's a rationalization of Gay-Lussac's law. Finally, we're asked to look at volume against temperature again at constant pressure. So volume against temperature at constant pressure. Okay, and this is an example of Charles' law. And what Charles' law says is that the volume is directly proportional to the temperature at constant pressure. Okay, V is proportional to T at constant P. As temperature goes up, so too does volume. As temperature goes down, so also does the volume as well. If we sketch that relationship, volume against temperature, we get a straight line, we get a proportional relationship between the two, again with our temperature in Kelvin, looking like that. Okay, so that's a sketch of the relationship between the two. Can we rationalize what's happening here? Well, again, imagine that we have a sample of gas and the roof of the container is a movable piston that looks something like this. So we have a fixed amount of gas in here, and let's imagine that we have a system at constant pressure. Well, if we change the temperature, i.e. if we add heat, what's going to happen? Our molecules are going to move faster, the collisions are going to become more frequent. But remember, now we've got constant pressure. And so what's going to happen? Well, in order to maintain constant pressure, the volume would have to increase, because it would have to counteract the effect of what the heat is doing. The heat increases the energy of the collisions, and it increases their frequency. So we have to increase the volume and to bring down the number of collisions, which is obviously going to decrease as the volume increases. So as the temperature goes up, the volume would also have to go up as well, which describes this direct proportionality that we see between the volume and the temperature over here as sketched by our diagram, and we can rationalize a similar sort of behavior if we were to take heat out of our system. The volume then would have to contract for similar reasons. Okay, so that's a very quick rationale for 3 of the gas laws. The final part of this problem involves some calculations. And here we have a sample of gas with initial volume, pressure and temperature given, and we're asked to find out what happens to the volume if the conditions are changed such that we have a different pressure and a different temperature. Okay, in order to answer these types of problems, we first of all start off by noting down our combined gas law. P1 V1 over T1 is P2 V2 over T2. Okay, and the way that we address these problems is to write down what we know. Okay, P1 V1 and T1. Let's write down the information that we have. Initial pressure is 2.75 atmospheres. Initial volume is 256 milliliters, and the initial temperature is 16 degrees centigrade. And as I've already said, all of these gas law calculations must be carried out using the absolute temperature. So we need to convert that to Kelvin. That becomes 16 plus 273 Kelvin, giving us an initial temperature of 289 Kelvin. So we know all of our initial conditions. Our final conditions, P2, V2 and T2, are what? Well, the final pressure, P2, is 1 atmosphere. Our final volume is what we're trying to work out, and our final temperature is 100 degrees centigrade, which again we're going to convert to Kelvin to give us a final temperature of 373 Kelvin. Okay, so what is it we're looking to calculate? We're looking to calculate V2. Okay, and in order to calculate V2 we need to rearrange our equation so that V2 is by itself. And so what we're going to do is we're going to move T2 up onto the numerator of the other side, and we're going to take P2 down to the denominator of the other side. That's going to leave us with V2 by itself being equal to P1 times V1 times T2 divided by T1 times P2. So we know all our conditions. We now have an equation that we can use. We then have to plug in all the numbers. P1 is 2.75. V1 is 256. T2 is 373. And then we're going to divide that by T1, which is 289. And we're also going to divide by P2, which is simply 1. And if we work that out, we get a result of 909 for our volume. The units will be the same as the units for our initial volume, which is milliliters. Okay, so the final result of this calculation says that the final result, the final volume in this case, is 909 milliliters.